So I want to quick talk about starting to work towards actually coming up with three-dimensional equations. I want to talk about lines in three-dimensional space, and maybe the easiest way to write them, to write lines. The first box, which you see in purple, this is called a parametrization of a line in three-dimensional space. And it should look like parametric equations, where we had an x equals with a t as a variable, a y equals with t as a variable, and now we've added a z. So this is the parametrization of a line. What you see below that in the green box is what's called the symmetric equations of a line. And you could see in every single case that it's just that every single equation has been solved for t. So subtract this, divide by a. Subtract this, divide by b. Subtract this, divide by c. And because all of them are solved for t, they're all equal to the same thing. They're all equal to each other. All right? So finding the line through the point and parallel to that vector. So we know how x is changing. We know how y is changing. We know how z is changing. We want it to go through this point. Here's the easiest way to handle this. X equals, I want this thing to start at 1 and apparently have a slope of -2. Y, I want to start at -2 and I want to have a rate of change of 7. And Z, I want to start at 4 and have a rate of change of -3. So you can see now my parametrization. I said I want to start here, and I want these things to be the rate of change in x, y, and z. So I've now built this line. And when t is, let's say, 0, I'm at the initial point. When t is 1, I begin moving. 2 units back in x, 7 units over in y, 3 units down in z. Now, the symmetric equation, again, we just go back and we solve every one of these for t. So subtract the 1, divide by -2. Add the 2, divide by 7. Subtract 4, divide by -3. And because they're all equal to t, they will be equal to each other. So your symmetric equations would look like this. Okay. Find the line that through those 2 points. Okay. Let's do this one with a parametrization, and you could really pick any point. I'm going to start. With this point right here. Okay. And I'm going to move. So I'm going to just put S. I'm going to move then to this point. S for start. So X equals. I start at 3. Now you'll note, and we could even do this all the way. We could say y starts at 4, z starts at 6. Okay. Now you'll notice that I started at 3, and then I decreased 5 units to -2. So the easiest way to do this is to just write minus 5t. And then we have to be, just kind of consistent. We'll notice that we were at 4, and we needed to decrease 3 units to be at 1. So we just do that. And here we were at 6, and we need to decrease 6 units to be at 0. Okay. Now, people will say, well, why does that work? Because it seems almost too easy. Well, think about this. We've defined all of these as a function of t. So when t is 0, I'm at the initial point. When t is 1, I'm at this new point. And I can just then continue building the line by changing the value of t. But it'll always be increasing, or it'll always have the correct and consistent slope.